Hello, Algebra 2 Trig students. This is Mrs. Leopold here. We are now on Unit 6, Parent and Piecewise Functions, and this is Lesson 1. I have a feeling this is going to be a long lesson, so feel free, of course, to skip ahead to what you actually need or to put me on double time if I'm talking too slowly. Up to you. But let's jump in. We're going to look at a bunch of graphs today, and we're calling them parent functions, and then we're going to apply our transformations we've learned earlier in the year to each of these parent functions and either try to graph the function based on the algebraic function that we're given. We're going to make the graph, or we're going to see a graph and we're going to try to develop the algebraic function. So the first one here is the square and the square root function. Well, you've studied the square f of x equals x squared quite a bit. In Algebra 1, you studied it. In our first semester, we studied it quite extensively. Hopefully, you remember that it's rooted here at 0, 0, right? That's the vertex. And when you plug in -1 and square it, you get +1. If we plug in -2 and square it, we get +4. If we plug in -3 and square it, we get +9. So we go left 1, up 1, left 2, up 4, left 3, up 9. And of course, if we square 1, we get 1, 2 squared is 4, 3 squared is 9. So oftentimes when I was teaching it, I was calling it the 1 to 1, 2 to 4 method, right? So you go right 1, up 1, left 1, up 1, or right 2, up 2, left 2, up 2. It's reflective over the y-axis. It's symmetric with respect to the y-axis. So that's your basic f of x equals x squared. Now, what happens if we do g of x and take the square root of x? How are these related? Well, hopefully what you're saying to yourself is, I want to take perfect square numbers for x because I can take the square root of 0. The square root of 0 is just 0, so we're still going to have this point on it. I can take the square root of 1, right? If I choose x as being 1, the square root of 1 is 1. Or how about 4? That's my next perfect square. The square root of 4 is 2. My next perfect square is 9. The square root of 9 is 3, right? I'm plugging in the value of x, and I'm then taking the square root of whatever that value is to get my y value. So right now, g of x equals square root of x. We would have the point 0, 0, 1, 1, 4, 2, 2, 3, 4, so I'm trying to count and talk, and 9, 3. Now, what happens if I put in -1? Can I take the square root of a negative number? No. The square root, of -4. No, those don't exist, so those aren't possible. So the only graph that I'm going to have is when I put in positive x values, the square root of a positive value is a positive value, right? And if I put in, like, say 2, if I put in 2 here, well, the y value is square root of 2, which is approximately 1.7 something, so that's when you put in 2, you go up, or it's 1 point, I don't know, whatever it is. You can plug it into your calculator. But the easiest points to graph are going to be these. Now, what might you notice about how are these two related? Hopefully you're saying to yourself, you know what? They kind of look like inverses of each other. Remember, inverses are when you take the ordered pair x, y, and you switch them, right? So this ordered pair here, 0, 0, is over here. This ordered pair, 1, 1, 2, 4 became 4, 2, 3, 9 became 9, 3. And so, but what about all these negative values? Did those switch? No, they didn't. So they're inverses of each other almost, except we're going to have to do what here? It's only the right-hand side of the square function that's going to be the inverse of the square root. So remember back in semester 1 when we talked about limiting the domain, this is what we'd have to do. So yes, they would be inverses of each other if we limited f of x's domain, right? That would have to only go from 0 to infinity. So we can only take the right-hand side of x squared, and then those two functions would be inverses of each other. All right, how about a cubic and a cube root function? How is that different than a square and a square root function? Well, I don't know. Have you ever studied a cubic before? I'm not sure. So let's just put in some negative numbers and some positive numbers. If I put in -2, -1, 0, 1, and 2, so plug in 0, or plug in -2, sorry, we're going to get -2 cubed, and a -2 times a -2 times a -2 is -8. -1 cubed is -1 times -1 times -1, which is -1. 0 cubed is 0. 1 cubed is 1 times 1 times 1, which is +1. 2 cubed is 2 times 2 times 2, which is +8. And we could continue. But if we graph those ordered pairs, we'd have 0, 0, -1, -1, sorry, -2, -8, 0, or -1, -1, 0, 0, 1, 1, and then 2, 8. So your graph of a cubic function looks something like this. I don't like my graph so much. I'm going to do it again. Graph of the cubic function comes up, squiggles through. This is continuous through there, so it's curving through, and it looks like this. What do you notice the domain is? The domain is all real numbers. What is the range? The range is also all real numbers. Okay, awesome. Now what about the cube root function? So g of x equals the cube root of x. So we need to choose numbers that we can take that you can take the cube root of them. So in other words, 8 is a perfect cube. It's 2 times 2 times 2. So if I put an 8 for my x value, well, the cube root of 8 is 2. If I choose a 1 as my x value, the cube root of 1 is 1. The cube root of 0 is 0. So basically what happened to my x and y coordinates here? They are reversing, right? So we have, these are inverses of each other. These two functions are inverses of each other. So I'm switching the ordered pair. So this time I go to the right 8, 1, 2, 3, 4, 5, 6, 7, 8, up 2. I go to the right 1, up 1, 0, 0, -1, -1, and then -8, -2. So this time it's going to come through, and my purple graph is my g of x function. Now, if you recall, I didn't say this last time, but your inverse functions are reflective over the line y equals x. So these are inverses because I could fold my paper on this green dotted line, and the blue graph and the purple graph would lay right on top of each other. So these are inverses of each other. Every x and y coordinate will switch to its opposite, right? So these x comma y's will switch, and the 8 becomes the x coordinate, and the 2 becomes the y coordinate. So how are they related? They are inverses. All right, now we have the absolute value function. The absolute value function, f of x equals the absolute value of x. Remember, these symbols mean the absolute value. That's something you should have studied in Algebra 1. You probably just haven't talked about it for a while. But when we talk about the absolute value, what do we actually mean? We're talking about the distance from that number to 0 on the number line. And whenever we're talking about distance, distance is a positive value. When we throw a negative inside of it, that's a direction, right? So we have a positive direction, a negative direction, but the distance, when we're saying how far is it from point A to point B, we always give a positive result. That would be representing the distance. So if you choose some negative numbers and some positive numbers, when you take the absolute value, so the absolute value of -2 is just 2, because on a number line, right, -2, -1, 1, 2, the distance from 0 to -2 is 2 units. The distance from 0 to -1 is 1 unit. The distance from 0 to itself is 0, and the distance from 1 to 0 is 1, and then 2. So we have what points? We have a 0, 0 point, negative 1, 1, negative 2, 2, 1, 1, 2, 2, etc. So that's going to go on and on. It makes a V, right? So you should have a perfect V. You have an axis of symmetry. It's also symmetric with respect to the y-axis. So that is what your absolute value graph will look like. And notice the slope is equal to what? Well, on the right-hand side, your slope is equal to 1. That's your right-hand side slope. And on your left-hand side, the slope is equal to what? Well, it's equal to negative 1. So we'll talk about that a little later. Here are some common parent functions, right? So what do we see about the common parent functions? I'll just point out a few things. The linear function you have looked at before. Remember, m is representing the slope. The slope is rise over run. You also might think of it as y2 minus y1 over x2 minus x1. B is your y-intercept. That's the place where the graph crosses through the y-axis, right? So that's everything about the linear function that you studied a lot in Algebra 1. And then we have the quadratic function. You've studied that now in Algebra 2 trig and in Algebra 1. We call this point here the vertex, right? So what is the vertex? Remember, the vertex is h comma k. So it's these two values here. Remember the a value, that's your vertical dilation, right? So that tells you if you're going to stretch or shrink vertically. You might have a negative in front of that, which is going to be a reflection over your x-axis. Then we have our cubic function here. This is not called a vertex. We usually call this the center of the cubic. The center could also be referred to as hk, and the a value is also a vertical dilation, so it's associated with a vertical stretch or shrink. And of course, if that a is negative, you would also reflect it over the x-axis. This is your base of your logarithm. We have the exponential function, which we studied at the end of first semester, right? That's taking a base to an exponent, exponential growth. Remember, you have your base right here, and then of course your h and k is telling you how you're going to move the new x and y axes, so how many you move it to the right or left, how many you move it up or down, and then this is your vertical dilation again, or it's also associated with your initial value. Like here's your initial value, so if your initial value is 1, then you're just going to have no stretch factor, no vertical dilation, or an a value of 1. Your logarithmic we studied just recently, right? So this is your initial value. A will tell you impact your initial value. We didn't do any changes with that, but you could. Your base of your logarithm here. And then your h and k tell you how you're going to move your x and y axes to kind of get this anchor point and figure it out, what it's going to look like from there. And then we have our absolute value function. H and k, that's what impacts your vertex, right? So we call this a vertex as well in our absolute value function. And then your a is associated with your slope, and I would focus on the slope of one side. So over here, we can just say the a value is going to represent the slope on the right-hand side of the absolute value. And then our last three, which are new to you right now, I suppose, unless you've studied them at a different school or in a different curriculum, but we would still call this the vertex of a square root. So h comma k is your vertex. Remember, the square root can only have positive values underneath the square root, so it's only going to go to the right with all those positive values. And then this is your vertical dilation, so it's telling you if you're going to stretch it vertically. Your cube root function, again, this a value is your vertical dilation, right? A value is your vertical dilation if you're going to stretch or shrink vertically. And of course, your h comma k in this case would be associated with what we call the center. So we call this the center. Sorry, over here, we call it the vertex. And then your reciprocal function, you're going to study in pre-calc. So you can wait for that We will not be studying that this year. So let's look at example 1. Now that we've kind of reviewed all the parent functions, let's see how we can adjust them based on changing the S's and K's and the A's and stuff like that. So this first example, we gave you a graph and you have to try to come up with the function. So if you want to go back and look at those families of functions and ask yourself, is it a linear function? Is it a quadratic function? Is it a cubic function? Is it a cube root function? Is it a square root function? Is it an absolute value function? So right here, hopefully when you look at your parent functions, you say to yourself, you know what? This is a cubic function, which is an x to the third power. So my parent function is just f of x equals x cubed. But now I'm going to do transformations to this function. So when I do transformations to this function, that means I could have some a value in front, a stretch value. Then I could have some kind of impact, a right or left transformation. So that's my minus h, and then my placed k, which is my up and down transformation. So that is, we're trying to fill in now for a, h, and k. So the easiest point, hopefully you know to fill into, is your vertex or your center. So in this case, sorry, it's a center. So that's h comma k. So your center was typically here, right? So this was your original function. And if you don't know this yet, you're going to have to you're going to get to know it as you go through this unit. But your cubic function is just 0 cubed, 1 cubed, 2 cubed, negative 1 cubed, negative 2 cubed. Those are your values. Now what happened? We moved our vertex to the right 4 units and down 1 unit. So we moved it to the right 4 units and down 1 unit. So how can I rewrite the equation with this? Well, let me do that instead with the equation. So I'm going to do f of x equals a times x. If I move to the right 4, that's minus 4. And if I move down 1, that's going to be minus 1. So I have filled in my h and my k to these two positions up here. So that is my center. Now, to get your a value, this is the harder part. So to get our a value, we're going to choose a point other than the vertex, or the center in this case, and use it to calculate a. So I need to choose either this point here, which is 6, 1, or I need to choose this point down here, which looks like 2, negative 3. Okay, either one. So I'm going to take f of x equals a times x minus 4 cubed minus 1. Well, I'm going to choose 6, 1 because it's all positive numbers and I don't know, I'm just going to go with that one instead. So my y value is 1, so I plug in 1, and then I get my x value is 6, so I plug in my 6, and now I have to solve. So the first thing I'm going to do is add 1 to both sides. So I get 2 equals a, and then 6 minus 4 is 2, so I get 2 cubed. Well, 2 to the third power is 8, so I get 2 equals to 8a. Divide by 8, so a equals 1/4. So my final function, oh sorry, and I see here it should be all of g of x's, apologies, would be g of x equals 1/4 times x minus 4 cubed minus 1. So I first used my translation to the right and down to identify what my h and k are. Then I chose a point on that graph to calculate to find my a value, my vertical stretch value, and then I went and plugged it in and got my a value. And there we have it. All right, moving on. We have 2 graphs here. The first thing you need to do is kind of figure out what is the parent function, right? So if it's starting at a vertex point and going up and to the right, hopefully you're saying to yourself that parent function is the square root of x. Go look at your parent functions at the beginning and notice this one is what it takes after that square root of x function. It looks like this. So, but clearly we have some kind of vertical stretch going on here, but we need to figure out what that vertical stretch is. So the first thing though, before we even do that, would be to relocate the vertex. So we went to the left 4, down 6. So my vertex is -4, -6, and I'm going to insert that into my function. So it's f of x equals the a value, which we don't know, but I moved to the left 4, so I put a +4 in there, and I went down 6, so I put -6. Now this is the general equation of that function, but I need to find the a value. So to find the a value, I'm going to use this y value of 0, 2. So when x is 0, y is 2, and that's going to allow me to calculate and solve for a. So when y value is 0, sorry, when the y value is 2, the x value is 0. So the first thing I need to do is add my 6 to both sides. So I get 8 equals the square root of 4. Well, what is the square root of 4? That's 2. So I get 8 equals 2a, therefore a equals 4. So the last thing I do is substitute in 4 from a. So this would be my equation of that function. Again, the first step maybe is the hardest one, and that's to decide what type of function it is. times 0, I get 5. Oh, look, there's that point. When I plug in negative 2, I get 2 times negative 1 plus 3. So that's negative 2, 1. Here's this point here. When I plug in 7, I get 2 times 2 plus 3. So 2 times 2 is 4. 4 plus 3 is 7. So I get 7, 7. Here's this point here. So that worked. My prediction was correct. When I plug in negative 9, I get 2 times negative 2, which is negative 4, plus 3, which is negative 1. And there's my last point. So I connect them with a smooth curve, clearly showing the end of behavior, meaning showing that it goes on infinitely with those arrows at the ends. Fill out that graph, and there you have it. All right, example 5 is your absolute value function. Your absolute value is typically in this type of form, right? Or just y equals absolute value of x. So we have a new vertex, which is going to be 4, negative 1. So go to the right, 4, down 1. And then this really tells us what our slope is. And we go to the right of the vertex to do that slope. So if it's negative 3 halves, you're going to go down 3, right 2, down 3, right 2. And then on the other side, it's the reflection. So we would go the opposite direction or just reflect over here. So it's going to look something like this. So the slope for the graph, we go from the vertex to the right to do that slope. It only works on the right-hand side, and the left-hand side is the reflection over this line wherever the vertex is, right? Then we're reflecting it. So we don't need a table of values for the absolute value as long as you understand how to do the slope, but you have to go to the right of the vertex and implement whatever slope is given. It must be to the right only, and then you reflect that over whatever the vertex is to see from there. And that's it. So again, it's a negative in front, which means your reflection is over the x-axis, so it's going to open downward. And so this is what your graph would look like. If you need to, you can make your table. Right? You can do your x and y values. Once you get your vertex, which is right here at 4, negative 1, then you can plug in a 5, you can plug in a 3, and you can see what you'd get. Right? So 5 minus 4 is 1. So 5 minus 4 is 1, negative 3 halves times negative 1. That's going to be right here in the middle at negative 2 and a half. So that would also give us a point, which is fine. Or you could go 2 over and you wouldn't have a fraction anymore. So this would be negative 2 and a half, which is what we have here and here. All right, our next graph, our final graph is a cube, something to the third power, so a cubic. So typically our cubic function looks like this. So that's what you're going to try to have to memorize. What do your parent functions look like? And if you go back and look at the beginning, when you had your origin here, your center at 0, 0 at the origin, then we move to the right 1, up 1, right 2, up 8, left 1, down 1, left 2, down 8. Then what do we do when we only have a 1/2 here, right? So first, let's find our new center. So our new center is to the right, 3, up 2. So I go right, 1, 2, 3, up 2, right there. Now you can either do your table of values. So once you have that center, I would choose a number to the right and to the left of it, right? So if this is 3, I would be choosing 4, and I would choose 2 to see what's going on. You can plug those values in, or you can say to yourself, typically, you would go to the right 1, up 1. But with the half stretch value, that means we're only going to go up half that distance. Typically, we would go to the left 1, down 1, but we're only going to go half that distance. Now that's not three very good points. That's not going to show you your end behavior very well. So you might want to do 5 and 1, right? So you could plug in those values as well. Or when you go to the right 2 units, right? When we went to the right 2 cubed is 8. So typically we would go up 8 units. But when we go to the right 2 units, instead of going up 8 units, we're going to go up half that amount. So 1, 2, 3, 4. Left 2 units. Instead of going 2 cubed, which is 8, or down 8, we're going to go down half that amount, which is 4. So this is what my graph should look like. If you aren't sure, plug in the values to the right and left of wherever your new center is. So plug in 2. So 1/2 times 2 minus 3 cubed plus 2. Get your y value. 1/2 times 4 minus 3 cubed plus 2. Get your y value. 1/2 times 5 minus 3 cubed plus 2. 1/2 times 5 minus 1 cubed plus 2. Right, so plug them in, see what you get as your result, and then, oops, sorry, I don't know why I put 5 minus 1 here. Whoopsie. Should be 1 minus 3. Get that value, cube it, multiply by 1/2, get your answer. And you will find that they were these exact points over here, right? So we get 2 minus 3 is -1. -1 cubed is -1. 1/2 times -1 is -1/2 plus 2, which is positive 1/2. So when I went to the right 2, I only went up 1/2, and that is that point there. So you could continue solving these y values. You should get the y values I have printed on this graph. Do the math yourself. This would be on the non-calculator portion, so don't grab your calculator. Try to do that on your own. If you're not sure what I was doing beforehand with the right 2 up 8, right 1 up 1, please ask. Ask me, ask your teacher, ask another teacher, ask your mom or dad, look on Khan Academy, but we can help you figure this out without making tables. Okay, finally, we're talking about inverses. Remember, how do we find an inverse? Well, to find inverses, you have to switch the x and y, and then you have to resolve for y and substitute in f to the -1 of x. So inverse notation is f to the -1 of x. So this is your y value. We're going to make that an x. This is your x value. We're going to make that a y. So I switched my x and y. Now I have to resolve for y. So I move my 6 to the other side. Then I divide each side by 2. Then how do I undo a cube? Well, hopefully you're saying, okay, to undo that, I need to cube root both sides. So if the quantity of y plus 4 is being cubed, I need to undo a cube by cube rooting. So on the left-hand side, I'm going to get the cube root of x plus 6 over 2. And on the right-hand side, I now just have y plus 4. So my final step is to take the cube root of x plus 6 over 2, move the plus 4 to the other side, which becomes -4, and change my notation from y to f to the -1 of x. So this is the inverse of the original function. Now, if you were to graph that, if you have a graphing calculator, I'd go ahead and graph. You could check the table on your graphing calculator, make sure your x and y intercepts are switching to the opposite. So yeah, you could graph it, look at your table, compare. And for this last one, we have a square root function. Okay, so we're going to switch the x and y because we're trying to find the inverse algebraically. So first we need to switch for x and y, solve for y, and then replace it with the notation f to the -1 of x. So this is my y, so I'm going to make that an x. This is my x, so I'm going to make that a y. Great. Step number 1, switch the x and y. Now I'm just going to solve, so I'm going to move my plus 3 to the other side. So I get x minus 3 equals 1/4 times the square root of y plus 2. Then to get rid of this 1/4, I need to multiply by 4, which means over here I need to multiply by 4. So On the left-hand side, I have 4 times x minus 3. On the right-hand side, I just have y plus 2. Then, how do I undo or get rid of the square root? Well, to undo it, hopefully you're saying to yourself, I would need to square both sides. But when you square this, you have to square the 4, which is 16, and you have to square the x minus 3 squared. So I would get 16 times the quantity of x minus 3 squared equals y plus 2. My last step is to move that plus 2 to the other side, and in the same step, I'm going to replace my y value with the proper notation of f to the negative 1 of x. I'm going to move that plus 2 to the other side, so this appears to be the proper function. But that is not quite true. Sorry, side note here, some of you might have said, hey, why can't I do for x minus 12 the quantity squared? You can do that too. That would have been fine if you had distributed the 4 times the x and 4 minus 3 and then squared that quantity. That's fine. So this is 4x minus 12. That works as well. Yeah, so either of these answers are fine. Okay, but sorry, going back to, this is not quite the right answer. That's incorrect. Why? Well, if you look at this original function, if I'm going to graph g of x, oh sorry, this should be a g to the negative 1. If I'm going to graph g of x, I'm going to move my vertex left 2 up 3. So this is my vertex. Typically, it would be opening this direction. But notice, if I were to graph this function, I would go to the right 3, down 2, and this would be a parabola opening upward on both the left-hand side and the right-hand side. So why should alarm bells be going off in your head? Going, wait a minute, that doesn't make sense. If you only have the upper portion of your square root, you can only have the right portion of the square. And if you only have the right portion, because those are corresponding, and they would be reflective over this graph of y equals x. So the left-hand side is not part of the solution. So now I have to put a real domain restriction. So I'm going from this value here of 3, inclusive of the 3 to infinity. So it's only the right-hand side, right? So stop. When do you restrict the domain? You have to restrict the domain for a square root function. The cube root's okay. Cubes, you can take the cube root of a negative number, but you cannot take the square root of a negative number. So that is going to be limited. So here was my original function. It was only the upper portion because this is a positive value. So we only need the right-hand portion. So what is the right-hand portion? Well, that's limiting my domain from 3 to positive infinity. So when do we need to restrict the domain? When we have a square root function originally, or you're actually going to have to limit the domain when we do the absolute value. And we will talk about that in a future lesson. And finally, how can we use function composition to verify if the functions are inverses? Well, remember, if f of g of x equals g of f of x, and both of those equal x, then the two functions are inverses of each other. So let's try f of g of x. So f, and we're going to put in g of x, and we're going to see what happens. So f of x, sorry. All right, so what do we have? Well, f of x is this function right here. So wherever I see the x value, I have to put in g of x. So this has to be going in there. So I get the cube root of negative x minus 2 plus 3. That just all went in for this x here. So I have this part minus 3, and then that is cubed, and then plus 2. right? So I took this g of x function and put it in for the x right here. Now I need to simplify. Well, minus 3 plus 3 cancels. So I have the cube root of negative x minus 2, and that's cubed plus 2. A cube root cubed just cancels each other out. So I have a negative, well, these cancel, so I just get negative x minus 2 in here, and then plus 2. But when I distribute a negative negative x and a negative negative 2, becomes positive x plus 2 plus 2, and that is x plus 4. Did it equal x? No. So f of g of x equals x plus 4, which does not equal x. Therefore, f of x and g of x are not inverses. You don't even have to do the other direction. You don't have to try g of f of x because it's, even if it equals x, it doesn't matter, but it doesn't equal x in this case. If you had chosen that one, you would also get it not equal to x. So if they both don't equal x, or even if one of them equals x and the other one does not, you do not need to do anything further. You would just stop and say, this is my answer. Because it didn't equal x, they are not inverses of each other. Phew. So the doozy of a lesson. There's a lot going on here. I'd imagine you probably need to talk to your teacher here or there for some more tips. So please reach out. Don't necessarily rely on this video. Reach out to your teacher and ask questions. We're all willing to help. Bye.